So maybe for a little bit of motivation, why is this sort of a nice system, apart from what I'm going to show later about how it's sort of easier to use and more efficient and so on. But I'd say that sort of the main kind of technical points would just be that essentially the code that you get when you compile something is pretty much the same code that you get from kernel C code, which has a few advantages. First of all, it means that you don't have to do expression serialization and deserialization. So for instance, if you have code that's manipulating expressions, or say it's taking and returning expressions, as is very common in something like library link, you'd either have to do that by passing the expressions over through WSTP, which is both a pain because it's sort of not very user friendly, and it's also kind of slow because you have to be constantly serializing and deserializing everything. But if you do things through the compiler, that it's just passing around the expr struct, which would be much more efficient. It's also much easier and nicer to use because you have access to lots of much higher level functions for manipulating expressions that normally you'd have to write yourself if you were doing it in something like library link. Maybe one other thing I'll mention up front that's sort of a nice UX feature is that, unlike something like library link where you have to create all these interface files and you have to sort of leave the program, with the compiler you can do everything pretty much in the program. So you don't have to leave, if you're doing things in a notebook, you can basically do everything you need in a notebook without stopping your kernel or without writing external files or anything like that. So that's pretty nice. So let's start with maybe a very simple example. So the main symbol that makes a lot of this possible is this new symbol called library function declaration. So the way this works is, in the compiler, there are a whole bunch of different declarations, like there's function declaration and type declaration, and there's also library function declaration. And basically what all of these do, they're just these kind of inert symbolic wrappers that you can use, that you can give to the compiler, and that will sort of change its behavior in various ways. So in the case of library function declaration lets you declare a function whose definition is in some dynamic library somewhere. So with normal function declaration, you'd give it the name of the function, and then you'd give it a definition for the function, in compilable Wolfram language code. But with library function declaration, it's kind of the same idea, but you don't actually give it the definition. You just tell it where to find the definition in some dynamic library somewhere. So if we look at the usage line here, we can try and maybe make an example for this simple function that I found from the OpenSSL documentation. This is a very boring function. All it does is it returns the version number, but I think it's good to start with something kind of trivial. So looking at the usage line, basically the way library function declaration works is you give it the name of the function that you want to be able to interface with. So in that case, it's just this OpenSSL version num. You give it basically the path of the library, and then you give it the type signature of this library function. So for the path to the library, I'm going to do something a little bit naughty here, which is just that you can actually write automatic here. And what that basically does, it says that I as the user am going to load the library myself. So this doesn't have to automatically load it. If I gave it something like libcrypto as a string, it would call find library on it, it would find it, and it would load it at the appropriate time. However, I know in the case of OpenSSL that the kernel generally loads OpenSSL when it starts. So I'm gonna, for the sake of this demo, I'm gonna just write automatic there. And then I should explain this type too. So the way that types work in the compiler, the way you write a function type is you write a list containing the types of all the arguments. In this case, there are no arguments, so it's just an empty list. And then you write an arrow, and then you write the return type, which in this case is a C unsigned long. And this is a documented 13.1 new type, basically, which you can use in order to, this will turn into some sort of unsigned integer 64, or on Windows it would turn, I think, into an unsigned integer 32 or something like that. But right. So okay, so I can save this in a variable, and if I run this doesn't do anything at all. It just sits there completely inert. But what I can do is I can call function compile, and I can pass this in. So basically what you do is you put the declarations in the first argument of function compile, it's like this. And then the second argument, you give it the actual program you'd like to compile. So in this case, I'll give it a pure function. And in the pure function, all I want to do is I want to call this function that we've declared here and return the result. So the way that these functions get sort of automatically named when you declare them like this is using a new usage of library function. So what you do that only exists in the compiler. So what you do is you write something like this. So this object here represents this function that we just declared here. And so this is just a function, and so I can apply this to whatever arguments I want. In this case, this function doesn't take any arguments. And so I can just write something like this. So let me save this in a variable and I'll compile it. And we get back this compiled code function, which you can see takes no arguments and returns an unsigned integer 64, which is that unsigned long there. And now if I run this, it returns some big random number. I mean, it's not random. I did check, and this is in fact some fairly weird representation of the OpenSSL version number. So this did give a correct result, although it's a little bit random looking. So this is just a very simple example. I'm going to go on to some more maybe more useful examples. But are there any questions at this point, just so that we don't have, cascading confusion? All right, I can't see if there are any, if there are questions that you just pipe up, because I don't have the thing open to see like hands or anything like that. But I'm just going to move on to the next example though. Oh,
Christopher, sorry, yeah, maybe do you assign the library function declarations to a libdec variable? Does that has a news that you are going to explain later, or is an inert head at that point?
I'm not going to use this libdec variable later, if that's what you're asking.
Yeah,
I just do this because I think it's often it's too messy if it looks like this. So
okay.
Yeah. Good question. All right, I'm going to move on to the next example though, but feel free to ask questions whenever. Okay, so this is maybe a more useful example. So in this case, this is another function from an OpenSSL, and I just copied this from the documentation. This is a function that computes the SHA-256 hash of some array of bytes. So we can do basically the same thing here. We're going to make another library function declaration, and I'm going to use the same variable name, just not for any particular reason, but just because that's the conventional name I use. And we'll give it the name of the function. We'll tell it to just trust us that OpenSSL will be loaded. And then for the type signature of the function, I'm going to use again some new kind of types. So for this first one, for convenience, I'm just going to use this thing called C-string, which will be nice because it means I'll be able to take a Wolfram language string and cast it to this C string and then pass it into this argument here. The next argument is a C size T, and the next argument is I'm going to actually write it as a C array of C chars. So this thing here, this is a new 13.1 syntax for type specifier. So if I look at what this evaluates to, because the output form right now, the output form eventually will probably display nicely like this, but for now it just displays like this. But this is what this turns into. So basically what this represents is a parameterized type. So this is kind of equivalent to if you were writing in say C++, this would be something like C array bracket C char, something like that. So that's all that is. But okay, so those are the input types, and the output type is another C array of C chars. So the way this function works is it takes first a buffer of data to hash. It takes a parameter that tells it how long that buffer is, and then it will write back 256 bits or 32 bytes into this buffer, and that's how you get the output. So again, I'm going to maybe define this library function declaration. And now we can write a function that calls this. But in this case, it's going to be a little more complicated because in the previous example, we didn't pass in any arguments. Here, we need to pass in all these funky objects that kind of, take some work to create. And also, the output, we're going to have to convert that back into some sort of expression that can be useful. So let's start writing it. So we're going to have to call function compile again. We'll have to give it this library function declaration. And for the actual function that we're going to compile, I'm going to just say that it's going to take maybe a string as its argument. So this is just a Wolfram language string. And then let me maybe define a module because I know I'm going to need it later. So the first thing we need to generate sort of the plain text that we're going to hash. So we need to generate this C string object. So what I'm going to do is I'm going to make a variable called plain text. And I'm going to just assign this to, I'm basically going to cast this, this Wolfram language string to a managed C string. So I'm going to explain a little bit more about what this managed thing is later. But basically what cast does, this is a new sort of compiler only function that kind of does what it sounds like. It lets you convert between types. So oftentimes this is kind of a no-op on the top level because you're doing things like converting between a real 32 and a real 64, which there's no concept of that in the top level. But this is a concept that needs to exist in the compiler where types matter. So in this case, I'm converting this string into a managed C string, which we can actually pass into this C function here. Then the other thing we need is sort of a ciphertext buffer, right? Because we need to have this buffer into which it's going to write its results. And for this, I'm going to use another new construct. So I'm going to write create type instance. This is a function that's used for basically creating instances of types. As you might guess. So in this case, I'm going to create an instance of C array. Actually, I'm going to create a managed C array. Again, I'm going to explain what the deal with managed is in an example in a few minutes. The way this works is that if you go to the documentation for C array, for example, it will tell you about all the different constructors that you can use with create type instance to create a C array. So in this case, I'm going to use a constructor where you just give it the length of the C array, in this case 32, and then it will allocate sort of an empty, quote unquote, empty C array, of that length. So this will allocate some buffer into which we can write the results. And now we can actually call the library function and do everything. So if I write maybe library function, we'll give it the function name SHA-256, and now we need to apply this to its arguments. So again, the first argument that this function takes is the plain text. So we'll give it the plain text. The next argument it takes is the length of the plain text. So I can write string length of stir. However, again, because we're in the compiler where types matter, string length generally returns a machine integer, which corresponds to some signed integer 64. But we actually told this function it needs to take a size t, which is an unsigned integer 64. So I'm actually going to need to cast this to be the right type. So I'll just do something like that. And then finally, we need to give it the ciphertext into which to write the results. So if I just run this, it will, it'll populate the ciphertext, but we need to actually convert the ciphertext back into something that we can return to the top level that'll actually be useful. So I'm going to use another usage of create type instance, and I'm going to create a numeric array. And there's again a documented constructor for numeric arrays, or the numeric array type, I should say, where you can give it a C array and then the length of that C array. So in this case, I'll give it C array ciphertext, and I'll tell it that its length is 32 bytes in this case. So if I run this, we'll take a moment to compile. But basically all this is doing is it's just taking this argument, sort of wrapping it up in these sort of C types, passing it into the function, and then wrapping up the result. So now we get this compiled code function back, and now I can actually try running it. So if I try maybe giving it some string, hello there, and if I run this, it returns a numeric array. And if I say maybe normal of this, we get this sequence of bytes. We can check that those are correct maybe by using the built-in hash function, which I think I can just use like this. Oh, I need to tell it SHA-256. And we need to call normal on that. And you can see it's giving the same answer. So this is in fact working, which is always nice. And in fact, it's actually working pretty well, because if I do repeated timing on these things, you can see that the compiled version is like, I guess, like 500 times faster than the built-in version, which is also sort of nice. I believe that the built-in version, some of the hash functions are implemented through some sort of JLink thing that I don't really understand. I'm guessing that's why this is so much slower. If this was actually implemented in kernel C code or something, I'd imagine it would be about the same, or library link for that matter. It would probably be about the same speed, but it isn't. So yeah. So this might be another point at which I should ask if there are any questions or anything. Because I know that was sort of a complicated example. Yeah.
So that cast, is that giving the raw UTF-8M to the library to the OpenSSL function, or does it convert to UTF-8 or some such?
That's a good question. I believe it does do the UTF-8 conversion, which means that this example I've written here is a little bit unsafe, because this string length is the number of characters, not the number of bytes. But in the simple example where I just give it ASCII, it does work. So if you were writing this for real, I would say you'd want to use, well, there are a few ways you could do it. The easiest way is probably there's some hidden compiler function that you should never have to use that lets you sort of get the actual number of bytes in the UTF-8 representation of a string, as opposed to just the number of characters. But yes, that's a good point. All right. Let's see. Unless there's anything else, I'm going to move on to maybe another fairly different example that maybe sort of also shows how this managed thing works, and how you can create. Well, I should just show it. So there's this library called GEOS. So GEOS is a C library that basically it lets you do 2D geometry. So it lets you you can have points and lines and polygons and multi-polygons, and et cetera, and then it has lots of operations like you can compute their Boolean intersection, and you can compute their area, and all that kind of stuff. But the nice thing about GEOS is that it's very efficient. So for example, you can compute the Boolean intersection between polygons with tens of thousands of vertices in like a fraction of a second. Like it's basically instantaneous. Among other operations like that, which is pretty useful, especially for doing kind of GIS things, or things where you have geopolygons where they may have many vertices. So GEOS actually is the library. If you use like QGIS, the open source GIS program, it indirectly, all of its geometry stuff is based on GEOS, as well as I think Postgres, or like PostGIS is also uses GEOS. So just a little bit of background on what GEOS is. So in this case, I have GEOS installed, and I have it in some random directory here. But I'm going to start by just making a very simple link to GEOS that just lets us basically create a very boring piece of geometry, in this case, just a point. And then we're going to be able to represent that geometry in the top level and move it around and have it be reference counted and automatically freed when the reference count goes to 0 and everything. So let's try it. So here, these are these two functions that, again, I just got from the GEOS documentation. So this first one, you give it an X and a Y, and it will create a GEOS geometry object that represents a point with coordinates X and Y. And then there's also a function for basically freeing that GEOS geometry object when we're done with it. So we can try and write a library function declaration for this, but there's something else we have to do first, because you see that in the previous examples, all the types were kind of built-in types. We knew what a size t was, and an unsigned char star. We could represent all these types. But in this case, there's a new type that we've never heard of before called a GEOS geometry. And we need to have some way of representing this in the type system in order to use this. So what I'm going to do is I'll maybe make a declaration that sort of defines this type here. So in this case, I'm going to make a type declaration to define this new type. And there are a few ways I could do this. One way I could do this is I could go into the header file where GEOS geometry is defined. I could look at it, and I happen to know it's a struct. And I could declare this sort of product type is what it's called, which is basically the compiler name for a struct. And I could painstakingly, list out all the fields in the GEOS geometry type, of which there may be many hundreds. And I could, copy those into Mathematica and have sort of an analogous type. However, there are a couple problems with that. First of all, the odds of me making a mistake are pretty high. Second of all, it's extremely painful to do this and time consuming and kind of stupid. And finally, if they ever change the API, we're sort of in trouble, because maybe they'll change the structure of the struct, or maybe on some platform the order of the fields is different or something like that, and then everything will break. So what I'm going to do is something that's a bit lazier, but I think is actually in many ways safer, which is I'm going to declare the GEOS geometry type as an alias, and I'm going to take advantage of the fact that I happen to know that GEOS always passes GEOS geometry types as pointers. So you never actually need a naked GEOS geometry object. It's always just a pointer. So what I'm going to do is I'm going to declare it as an alias of this built-in type called opaque raw pointer. An opaque raw pointer is kind of what it sounds like. It's just basically a type that represents a pointer, where we're not going to say anything about what the pointer points to. It's just a black box. There's another type called raw pointer, which is a parameterized type where you can sort of tell it about, it knows what it's pointing to. But in this case, we're going to use this much more, general opaque thing. Right. So basically, this GEOS geometry type is just going to mean pointer, essentially. So now that we have this, we can actually write out a declaration for this function here. So maybe I'll reuse my name again. We'll make a library function declaration. And again, we'll just give it this name here. We'll give it the path to the library that we want to get this from, in this case, libgeos. And then finally, we'll give the type signature. So in this case, the type signature is going to be, it's going to take 2 C doubles, and it's going to return a GEOS geometry object. So that's the main creation function. And now I'm also going to write out the declaration for the deconstruction function. So I'll write something like this.
Does library implicitly mean C? Does it mean C all the time, or what's the?
So it means C compatible. It means C ABI compatible libraries is the most technical way I can phrase it. I mean, basically what it means is any library that you could.
Why don't we just take the C specifications then for types instead of like inventing another string name for them?
You mean, why don't we just call this double with a lowercase d? Is that what you're?
Yeah. Or these longer ones, we could compile it into that, if we want that C, duration there, C dub,
I mean, I guess we could actually do that. I mean, usually, so so far I've been mostly using these sort of C types, but there are lots of built-in types. I mean, like, for example, list vector, or, packed array, or, integer 64. And the usual convention is, uppercase first letter.
Yeah.
So, I mean, we could, there wouldn't
I'm
be
ju-
any collision.
Right. I mean, that makes sense if you think of the internal ones, but I'm just thinking of, if we're thinking of as a kind of a friendly way to minimize the impedance mismatch, which it is doing.
Mhm. Yeah, you know, I think I think that
Uh,
would be doable. I mean, it's definitely doable from a technical perspective. I mean, the other thing is, I think that this is sort of my, you know, don't promise things, but what I imagine is in the, you know, eventually the way this will work is we'll have something that reads header files automatically and generates the library function declarations itself, and you
Right.
won't have to do that. So I think that's the end goal. So
I
you
see.
just point at a header file, and of course there's some choices that it might have to make, but it would just generate a giant list of type declarations and library function declarations. You can go through and you know, edit things if there are any sort of, because there's some cases that are truly ambiguous, like is this a pointer or is it a C array? But you know, you can kind of work those out, and then yeah, I think that's the ultimate end state. Yes.
Okay.
But okay. In any case, in the meantime, I have to write it like this. So right. So okay, so we have that function there, and then we also need the deconstruction function. So it's basically the same deal. I'm just going to give it the name of the function, the library, and then the type. So in this case, it's going to take a GEOS geometry object, and it's going to return void. Because it says void here. So right, so those are our functions, and now we need to actually, you know, call them. So again, we're going to call function compile. I'm going to give it all of these declarations. There's some ways I could declare these up front, and I wouldn't have to, you know, copy them down and so on. But I'm just going to do it like this for now. And then let's write the actual function. So in this case, our function is going to take two arguments. It's going to take an x and a y, and they're both going to be these sort of C doubles. And for the body of the function, well, the first thing we want to do is we want to call this create point from xy function. So just like before, we're going to write library function and then give it this string. And this is, you know, this represents that function that we got, you know, that they were loading from GEOS. So I'll just give this our x and y, and this thing here then represents this GEOS geometry object. Now, the problem is it's a little bit, you know, I don't want to just sort of return this, or I can't really return this to the top level because it's sort of just a pointer. I mean, first of all, it doesn't actually know how to represent itself with an expression. But the more fundamental problem is that, you know, it'll be a memory leak. You know, that I'm just allocating a thing. I have no plans for, there's nothing to manage it. So what I'm going to do is I'm going to actually use this thing called managed, which I used earlier in a slightly different way. And basically the way managed works, managed is a type that you can kind of wrap around any other type, or you can wrap around types that are not already memory managed, and the managed type will sort of add memory management to them. So this is a little bit analogous to the, or very analogous to the library link managed expressions business. Basically what this would do is it'll create an expression that we can return to the top level that will, you know, be reference counted. When its reference count goes to 0, it will call some provided destructor. So in this case, basically the way I create one is I say create type instance. I tell it I want to create a managed object. I give it the object I'd like to manage. So in this case, this GEOS geometry object. And then I just have to give it a pure function to call when I want to destroy this thing. So in this case, it's pretty simple. I'm just going to call this this destroy function, which again I just write with a library function like this. I'm just going to call destroy of hash, and I'm just going to, for the sake of demonstration, I'm going to add an echo here, just to you know, in a kind of random spot, just so we can actually see when this destruction function is actually called. So I'm going to run this, and it's now compiling. And so what this should give us is a compiled code function that again takes, you know, two two doubles or real 64s in this case, and returns this managed GEOS geometry object. So now I can try actually calling it. So maybe I'll do something like this, and you see we get back this object that looks kind of ugly and should look prettier, but right, this is just sort of an opaque managed expression object. And so I can move this around. I could pass it into another compiled function that takes a managed GEOS geometry object, which could process it and do whatever it wants with it, etc. But the nice thing that I want to kind of emphasize is the fact that this is actually like properly memory managed and everything. So if I put this in, for example, a do loop, we can see that it prints freed 5 times. So it did, in fact, it created this object, its reference count went to 0, and then it freed it. And it just basically called this arbitrary piece of code that we gave it, which is pretty nice. So, right, I mean, I think this is a bit less boilerplate than, for example, the managed expression business, where you have to register them, and then you have to have some way in C or whatever language you're using to sort of keep track of the different, what the index is, which objects correspond to which indexes, so that when one is requested to be freed, you can free the right one, et cetera, et cetera. So here, all you have to do is you just have to give it a pure function to call when you want it to be freed, which is pretty easy. Yeah. Again, if there are any questions, now is another good time to maybe go ahead.
So when you declared the return type to be the string void, could you also have done an empty list, or?
Yeah, so this is a bit of a thing I was going to gloss over. So I could not do an empty list because the way that these the list is just the template for functions is always just list arrow return type. So the list doesn't really mean anything. It's just used for functions. Void though, void is kind of a weird business though, because in general in the compiler's type system, we kind of don't really have void types, or as in like there always has to be something there. Like maybe you can return like the null type. The null type is it's a type with only one element, has no parameters. It's just like an empty struct kind of thing. But void is a weirder kind of low-level LLVM concept that kind of defies how you might think types work. But sort of for the sake of interfacing with other programs, and for the sake of interfacing with some LLVM functions that are needed internally, we do have this void type. Yeah, right. So no, you couldn't put an empty list. You have to put void there. But this void thing is a little bit of a funky object. So yeah.
Okay.
All right. So I'm going to go on to the last example here. So what I've done is in this case, I just wrote some, this is a pretty trivial function, and all it can do is it can create points from pairs of x's and y's. But what I've done kind of, quote unquote off screen, I can show anyone if this is interested. If anyone's interested, I can show this. But I wrote a big long program that basically will take in an expression, and then in the compiler, it will sort of rip apart that expression and process it in all sorts of ways. And then as it sort of rips it apart, it will call all the appropriate GEOS functions in order to, to build up the corresponding piece of geometry. So for example, I could give it a polygon expression, or a list of a polygon and a line, or whatever you want. And it would then go ahead and call all of the GEOS functions necessary to then create the corresponding geometry in GEOS. And I also wrote the function that goes the other way. So you give it a GEOS geometry object, and it will assemble it into the corresponding expression. So for example, I can run something like random polygon, get some, random piece of geometry. And then I have this function toGeos, which basically takes this expression, rips it apart, and turns it into a GEOS geometry object. And then I can call out from GEOS, and it will convert it back. And you see we get, basically the same polygon back. And And this link is like super efficient. There's no serialization of any kind going on here. So I mean, it's very well, I mean, I guess I am kind of serializing things to expressions and back again, or to GEOS and back again, if that's how you want to think about it. But the point is there's really no intermediate representation here. It's just directly calling all of the kind of low-level GEOS functions for constructing geometry, and at the same time for the expressions, it's just calling, you know, the low-level, basically kernel C code functions for constructing expressions. Although I would argue that the interface is a bit, it's often a bit nicer than the way you'd have to do it in kernel C code. But yeah. So now that we have this, we can now maybe do a slightly more interesting GEOS function. So the previous example, we just created a point, but this is an actual operation in GEOS. So this is a function called GEOS buffer. I mean, they have tons of random functions, but this is just a random one I chose because I think it's, you know, it looks cool. And basically what it does is it basically does the same thing as, it's like a more limited version and a more limited discrete version of region dilation. So essentially what it does is you give it a piece of geometry and you give it a diameter, and it will kind of like fatten up your geometry by that diameter. You know, this is also known sometimes as like a Minkowski sum with a disk or something. But right, so let's try and actually connect to this though. So let's see. Right, so what I'm going to do is I'm going to, again, we'll define this function. We'll call it buffer, and well, we have to give it all of our. Oh, sorry, I forgot. We need to first create the declaration, the library function declaration for this GEOS buffer function. So the way we're going to do that, well, it's the same thing as always. We just give it the name of the function, the path where it can find the library, and then the type. And in this case, the type is just going to be it's a GEOS geometry object in the first argument, you know, a double in the second argument, and an integer in the third. And the whole thing returns a new GEOS geometry object. There we go. So okay, so first we give it the declarations. So it's just all of these declarations we have here. And now for the actual function. So this is going to be pretty much the same as the examples we saw before. We're basically just going to give it, we're going to say that we're going to take a piece of geometry as an input. It's going to have type managed of GEOS geometry, because that's going to be the return type of that to GEOS function that I have above. And for the actual body of it, all we're going to do is we're going to call this GEOS buffer function, and we're going to give it first the geometry, and then the next argument is the width that we want to buffer by. So actually, sorry, I should have included that as an argument. Let me try and quickly format this a little bit. Yeah. So then we're going to take the width, and this is in the form of a double, and then we'll also maybe take this segments thing, and we'll take that as an int. So basically, what's this last parameter? I don't totally understand how it works, but it basically determines because this does everything discretely. So it determines, you know, if I had a point, for example, and you imagine I'd buffer the point, I'd get back a disk. So the question is, how many vertices should be on that disk? Like how high resolution should it be? So that's basically what this last parameter is. So okay, so we'll give it the geometry. There it is, and then we'll give it the width, and we'll give it the number of segments. So you can just pretty directly call this thing. There's really not a lot you need to do. The only thing that's left to do, though, is that this returns a GEOS geometry object. But as we sort of talked about before, we don't want to return a kind of naked GEOS geometry object. We always want to wrap it in this sort of memory management thing. So just like before, I'm going to say create type instance, and we're going to create a managed object to wrap this. And just like before, I'm going to, for the deconstructing function, I'm just going to call this GEOS geometry destroy, and I'm going to pass in hash. So now right, so if I compile this, so again, this function, all it's doing is it's just taking these arguments, passing them directly to the C function that we just declared, and then wrapping it in this managed object. And again, we get a function that takes a piece of geometry and some other parameters and then returns a piece of geometry. And so I can try running this. Maybe first I'll generate a random polygon. Maybe a better random polygon. There's a good random polygon, and I'll buffer it. And oh, whoops, sorry. I have to give it the parameters. Maybe I'll buffer it by 0.1, and then I don't know, 5 segments. Oh, sorry, I have to call to GEOS to turn this into a managed GEOS geometry object. Okay, so we get back a GEOS geometry object, and I'll call from GEOS to convert that back into a polygon. Of course, you could automate this, but in this case, I haven't. And you see, well, we get back this kind of fattened up version of the polygon. So maybe I'll make a nicer version of it. Maybe a blue. So the red region is the region that was generated by GEOS, and the blue region was the input one. So maybe just to do a slightly flashier version of this, I have this piece of code here that should give me a slightly bigger piece of geometry that's a bit more complicated. So this is a multi-polygon, and we're actually going to get a multi-polygon with holes and all this kind of stuff. So this is just a polygon for Massachusetts, and I can write pretty much the same code here. Let me actually just copy it down. So we'll give it, instead of poly, we'll give it mass, and I happen to know that the radius I should do is I should do a smaller radius like that. If I run that, you see we get this buffered Massachusetts, and you can see we have all this nice stuff like the buffered red polygon. It's a polygon with holes that are all represented correctly and all that fun stuff. And maybe just to make it even fancier, we could do something like wrap this in a manipulate, and maybe we can change the radius from, I don't know, 0 to 0.01 or something like that. And now I should be able to drag this and sort of get this dynamically buffering Massachusetts. So yeah, and you can see, we have all these, all this good stuff of where it switches from a multi-polygon to a multi-polygon with holes to a to a single polygon, and et cetera, et cetera. So yeah, so that was the last of the examples I have. I'm happy to answer any questions or anything, and also I might also recommend that there's a documentation tutorial that I think is also very useful and shows a lot of the same stuff I've shown here. The tutorial, I think, uses the example of SQLite. So it sort of makes a connection to SQLite where you can have, database objects that you can pass around in the top level, and then you just have a function for querying them, and the queried objects come back as, these beautiful expressions that are, lists of associations and stuff like that, and so on. But yeah, I think that's all the examples I have for right now.
Hey, Christopher, there's a question in the chat.
Let me take a look. On the first random polygon example, the polygon from GEOS had an extra point. Was it expected? Let me take a look at that. That is interesting, and my guess is there are 2 places this could come from. One place is it could be a bug in my code for converting things back and forth. The other option is that in order to pass things to GEOS, I have this, I call canonicalized. I think I call canonicalized polygon, and I do a few other. Actually, no, sorry. I think I avoid canonicalized polygon, but I do some other operations that kind of canonicalize the polygon in some ways. And so my guess is that that's where that extra point comes from. And if I had to guess, I'd also guess the extra point comes from something like I'm not sure if. So in Mathematica, the first point of a polygon doesn't have to equal the last point, and I'll just draw a line between the last 2. I'm not sure that's the case in GEOS, so that would be my guess about what that's about. But presumably it should undo that operation when you call from GEOS anyway. So yeah.
So in your destructor argument, you're consistently calling, library function of pound semicolon. And I'm curious about why, why that whole thing is necessary.
Right. So this is a good good catch. So right. So two things here. So the first thing is that if you're doing this sort of for real, there's a nicer way you can do this, which is if you just omit this whole argument, then what it'll essentially do is it'll attempt to call, well, it'll basically defaults to trying to call delete object on the object here. And so what you can do is you can define delete object for example, the GEOS geometry type. And now every time you want to create a managed GEOS geometry type, you just write it like this, and it will automatically, it'll know how to delete it. And so that's the real way to do it. But why did I write this stuff here? This is for kind of a stupid reason that hopefully should be fixed in like 13.2 or something. But basically the problem here is that the type it's expecting for this function is it's expecting something that takes, right. If this object here has type T, then what the expected type of this function is, it takes the T and returns null. But of course, that's not always the case, right? I mean, if I took away the semicolon, we wouldn't have null, we'd actually have void, which is a different type, or it doesn't even have to be void. Maybe it returns an error code or returns an integer or something like that. And so that's the problem, is that the types don't actually line up when you don't put a semicolon there. But there's a solution to this, which is just that it shouldn't expect, a null as the return type. Instead, it should just basically say, I need a function that takes a T and returns anything at all, because I'm going to throw it away. So that's what it should really do. But there was some issue with the type inferencer that in the last version, this was kind of at the near the freeze date. And so basically we just, basically you have to make it actually return null, which is why that semicolon is there. All right, well, if there aren't any other questions, I think that's probably about it. Maybe I should also mention that, well, if anyone's interested, I have a whole notebook with a bunch of these GEOS functions. Maybe I can tab over to it really quickly. So I mean, I have the, well, right. So the way it works is that this is the code that's very long, but also not particularly complicated. That this is the code that actually does the conversion between expressions and GEOS geometry objects. It's just long because it has a lot of cases to deal with. There's nothing particularly profound here. I mean, all it's doing is it's doing things like, here you see this function takes an expression and returns a GEOS geometry object. And so it's doing things like it's asking, what's the head of the expression? If it's a polygon, then, I'm going to want to create, a GEOS polygon object. And if it's a, line, I want to create a line object, et cetera, et cetera. And there's just a lot of cases to deal with. So that was that code that I sort of invoked earlier. And then all these operations, they're pretty simple. I mean, they're basically all we wrote here. You just declare the function, and then for the actual, program that you're compiling, you're really just calling that library function with the arguments, and then maybe wrapping this managed thing around it. And the results are pretty neat. So I mean, again, we had that buffer example, but then there's also stuff like, here's convex hulls and Delaunay triangulations and Voronoi meshes, and here's a big region intersection that runs, in a fraction of a second, and so on. So yeah, so I can, if anyone's interested, I can also share where to find this notebook and so on. But yeah, I think that's probably, yeah, go ahead.
Yeah, I have actually a couple more questions. So the first one is, I guess, feeding off of Roger's question. So this would only work with C++ libraries that have an extern C API, or?
Yes.
Okay.
Yes. I mean, I think there was some stuff, I looked into this recently about whether we could basically do the mangling everything. There's some parts of it that are a total nightmare. and there are also some things like methods for classes that we don't really have a way of representing right now. But so I think representing C++ stuff directly is I mean, of course, it's probably possible, but it's pretty difficult right now. So for now, I think it is pretty much CABI compatible libraries.
Okay. And then this is a very open-ended question, possibly another whole talk, but you sort of, right, you've given us these sort of concrete examples of how to call functions, but if we were to actually want to integrate a whole library, do you have sort of an overview of the workflow of, you know, starting from we've now compiled this external library. What do we do now to actually integrate this into the build?
Yeah, so I mean, well, there are 2 points there. I mean, one point is the pure programming point of how do you make, how do you actually write the interface and have, package up the library in a nice way. The other point is maybe about how do you actually build it. So for the how do you actually build it, this is I don't really know much about this. I know we do builds for this. In fact, this GEOS stuff, there's a packlet. There's a packlet where there's a version of all this GEOS code. I'm going to actually update soon because the current version is a little bit older. But there's a packlet that has all this code in it, and it's built. So like we have builds of this GEOS packlet that you can just load and call these GEOS functions from it, and it contains the GEOS library as well. So there are ways of doing this that I don't understand because I generally don't understand how builds work. But in terms of the programming process also, I mean, I'd say that something like this is pretty darn close. I mean, you can pretty much imagine how you would you just have to call these two GEOS from GEOS functions yourself and do a bit of error handling, and you'd be pretty much there. I mean, otherwise there's this example. Let me see if I can find it. It's the calling external libraries from the compiler. This tutorial shows a lot of the same things that I just showed, but mostly for this SQLite example. There's a little example about generating random bytes with OpenSSL, and then here's SQLite. So we have it so that we have a packlet that's just for this tutorial where you can download SQLite. And then let me see. So here's scroll down a bit. I'm gonna this is doing very similar things to what we were doing before, although this has a bit more expression manipulation and so on. But you see that this is the complete code, this here, and this just produces these two functions. One of them opens a database object, and one of them queries it. So you can call open, and it'll create this managed SQLite DB, just like we had the managed GEOS geometry object, and then you can query it, and it returns a list of associations for every row. So right, I think that it's I mean, one of the nice things about this is that it's pretty easy to like cherry pick a single function, like some of those earlier examples with OpenSSL, where we didn't, because there's not very much boilerplate. It's pretty easy to just pick out a single function from a library, but it's also not too hard to to get all the functions in the library. I mean, even this GEOS example covers most of the kind of beefy functions. I mean, the rest of the functions in GEOS are pretty much they're kind of busy work functions. Yeah.
Okay, thanks.
All right. Well, it looks like this is actually going to end almost exactly on time. So yeah, I think that's probably it. And of course, feel free to email me if you have any questions or anything. And yeah,